In this video, we continue some revision of the theory of Lie groups. I will remind you several formulas linking the adjoint map, the exponential map, and the adjoint representation. I will not prove them. You can try solving them as an exercise or look at my lecture notes. Afterwards, I will state the Campbell-Hausdorff formula, improve it in the case of linear groups. This formula will be important because it will make us write in exponential coordinates the product of the Lie group in terms of the operations on its Lie algebra. Let's see. We already recalled that if we have a group morphism, a Lie group homomorphism between two Lie groups G and H, then there exists an induced Lie algebra. This is a Lie algebra homomorphism that have the property that the diagram together with the exponential maps commute. So this is the exponential map, so it's the flow at time 1 of left invariant vector field. This is a group homomorphism, and this could be seen as the push forward of left invariant vector fields. Properly defined because this map might not be surjective or injective, but it is well defined as a push forward and extended as left invariant vector fields. So we know that this diagram commutes. Now we are going to see that some consequences of this commuting diagram. For doing that, I want to first review the adjoint representation and the adjoint map. Okay. So a little add from G to the Lie algebra GLG is the map that to every x associate what we called the add x, which is the map that to any y associate the bracket xy. Okay, and see that each of these map is a map that goes from G to G. So we can see it as an endomorphism of G. Okay, then quickly, okay, we have the conjugation map, the to G conjugate and every H to GH G minus 1. And I make you notice that the map that to every G associate CG, this is an endomorphism of G. I mean, the inverse is the conjugation by G minus 1. And then finally, the adjoint representation goes from G to the group GLG, and to every little g associate the map at G that to every x in the Lie algebra associate the vector push forward by CG of x. Remember, this map is a Lie group homomorphism, and therefore has a Lie algebra homomorphism associated. Actually, a Lie algebra isomorphism. Right? This is what it is, right? And again, the inverse is just add of G minus 1. Okay, now some more facts about these three maps. So facts. So okay, I already said the conjugation is a Lie group diffeomorphism, isomorphism. To add G, which is the the algebra isomorphism associated to CG. So add G belongs to the general linear group over G. Then the map to every G associated CG, this is a Lie group homomorphism. But the important part is this one, that the map to every G associated at G, this is a Lie group homomorphism. Therefore, one can consider the Lie algebra automorphism associated to this map. And one can prove that this is really little add. So this is a very important formula. It's not obvious from the definition, one should prove it. I'm not going to prove it. But yeah, so this is and of course, as a consequence of this formula, but could also be checked directly, the little add is not just a linear map, but it's a Lie algebra homomorphism. Actually, one can directly check this fact just by the Jacobi identity. Okay, but let's discuss more about this this formula. So, as a consequence, so let me recall. So what we have whenever we have a homomorphism, then you can pass to the Lie algebra to the associate Lie algebra homomorphism, and then you have this commuting diagram. Now, what does this gives in the case of the conjugation, for example? So if I take the conjugation, then pass to the Lie algebras. This is by definition is add G. Right? So this by definition, this was CG star. And here I always have the exponential map. So this diagram commutes. In other words, what I can write the formula, G exp x G minus 1 is equal to exp add G x. So I say exp x and then a conjugate is the same of taking add and then taking the exponential. Okay. Another consequence is, what about when we take the map add? Okay. Now the map add, let's remember, it's valued into the Lie group GLG. So whose Lie algebra is little GLG. We have the exponential maps and the Lie algebra of G is little g. So here we have add, which we said that by this formula, this is add star. And therefore we get a quite important formula. We get that, so this diagram commutes. So the formula is add after exp x is equal to exp, which is, okay, what is this exponential? This is the exponential of matrices. So let me write it as exponential matrix. So that e of add x. So I found this formula quite useful and important. All right, now let me write a sequence of formulas which more or less they all come as consequence of these two. Okay, so for some formulas after the exponential map Okay, so first I will just rewrite the previous two formulas, just to have a list of formulas. Exp add gx. This is true for all x in G. To add exp x is equal e little add x for all x in G. 3. Okay, these are other formulas that you can prove as an exercise, but they're really consequence of the previous two. This is exp of e add x at y. This is for all x and y in G. Another formula, okay, is about push forward of vector field. So if you take the flow of the left invariant vector field x time t, and with this you push forward a vector field y, then what you obtain is e to the minus add tx of the vector field y. This is for all x and y in G. Okay, to prove this formula, I'll give you the hint. The hint is that, remember, we already observed that this map here is equal to the right translation by the exponential of dx. Okay, so these are maps these formulas that, so these are formulas that hold in every the algebra of a Lie group. Okay, I'll point out other two, three formulas for the case of a linear group GLV for some vector space V. So if you take the adjoint of a matrix with respect to a matrix of another matrix, you can prove that this is just the conjugation. Now let's pay attention. So this is A. So A is any matrix, and instead B is an invertible matrix. 6 e to the add a of b is equal to ea b e minus a. Actually, this is true for all matrices a, b in GL. 7 e to the b a b minus 1 is equal to b e to the a b minus 1. And this is for all a linear map and for all b invertible linear map. Okay, I suggest you to do these exercises. I will now tell you a formula for the differential of the exponential map. It's very rare that in a course one sees this formula, so that's why I want to tell you about it. So let's start with something that is very important. That's why I'm sure you already saw it. We already recall it, that the exponential has the property that the differential of the identity, this is the identity on the Lie group. Okay, and one can draw a lot of consequences of this formula. But there is another formula that really tells us the differential at every point, not just at 0. And this is the formula. So the differential of the exponential map at any point x in the Lie algebra can be written as the differential of the left translation by x at the identity element, composed with the following linear transformation: the identity minus e to the minus add x divided by add x. Okay, let me clarify what is the meaning of this this writing. So here, for a equal to the adjoint of x, which is an element in GLG. I minus e to the minus a divided by a. You can see it as a formal series. So up is I minus identity minus the map minus the map square divided by 2 minus the map to the 3 divided 3 factorial, and so on, right? Divide by a. Okay, now as you see, the identity goes away, and then there is everything is a power of a. So just divide by a, and what you have is, so the first one is plus, so it comes to the identity, then it's minus a over 2, then plus a square over 3 factorial, minus, and so on. So as a series, we can write it as the sum of minus a to the k divided by k plus 1 factorial. Okay. In other words, this is really an analytic function. Okay. So we have this this formula for the differential of the exponential map. The proof is long. It's not very difficult. And with this, one can prove the following formula, which is important, and it's called the Bacon-Campbell-Hausdorff formula. So the Baker-Campbell-Hausdorff formula. We will just call it BCH for short. Now, there are many versions of the Bacon-Campbell-Hausdorff formula. I will state a very clean version of this formula due to Dynkin, and that I will state another formula for linear groups, and that is actually very easy to prove. So I will not prove the formula for the differential of the exponential map. I will not prove the Bacon-Campbell-Hausdorff formula for arbitrary Lie groups, but I will do it for linear groups. Okay, so but let me at least state the Dynkin's version of the Bacon-Campbell-Hausdorff formula. So suppose you have a Lie group, then for all x, sorry, the conclusion, for all x close enough to 0 in the Lie algebra of G, we have that the exponential of x times the exponential of y can be written as an exponential of a polynomial in x, y, and their iterated bracket, and the polynomial, sorry, a series. If it's not nilpotent, this might be an infinite series. So I will write it. So it's 1 over n plus 1 divided by n sum over ij 1 over I factorial, j factorial. These are multi-indices, norm of I plus norm of j. And here I need to put add x I 1 times, add y j 1 times, dot dot dot, add x I n times, add y j n minus 1 times, apply to y. Okay, of course, if this number is different than 0, then this is going to be 0. Okay, but so, and this formula is for I, j multi-indices and dimensional multi-indices, for which the sum of them is actually greater or equal than 1 for all k. Now, let me stress one thing. So very rarely you really need the formula. Very rarely the precise formula is important. What's really important is that there exists a formula. So in other words, the Lie bracket, the structure of the Lie algebra determines the product, at least in a neighborhood of the identity. Sometimes it's good to know the first terms. Sometimes the first terms are important, and I will write them later. Okay. But let's see the Campbell Hausdorff formula for linear groups, and I will prove it. So now we have G. This is a general linear group over a vector space. Then for all x, y in the Lie algebra, GLV, sufficiently close to 0, we have that EX, EY, I read it this way because this is exponential of linear maps, exponential. Okay, this also should be the same E, but I need to put something long as a variable. Minus 1 to the n over n, sum over ij of xi1, yj1, xin, yjn, all divided by I factorial, j factorial. Okay, and again, I and j are multi-indices for which the entries are greater than or equal than 1 for all k 1 to n. Okay, let's prove this formula. Proof. So the formula is obtained by formally solving for z in the equation z equal to ex times ey. In other words, z is log of ex ey. Now, because we have an expansion for the series of the logarithm near the identity, log of the identity plus a, this is equal to the sum minus 1 to the n plus 1 over n, an. Okay. So let's do it. So indeed, so what do we do? So z, as you said, this is the log of e to the x times e to the y. But let me write it as identity plus e to the x, e to the y minus the identity. Okay. Now I expand it and I have minus 1 to the n plus 1 divided by n, and I have e to the x, e to the y minus I to the power n. I can write the expansion of the series of e to the x, e to the y. Now the first term will cancel. This is I plus x times I plus y plus . The sum will cancel the identity, and then what is left is, so I can write it as x to the L factorial, y to the k, with k factorial, and the rest. So this is for L and K greater than or equal than 0, and none of them is 0. So now you can expand this other product and obtain the formula that I claimed. Let me stress what is the importance of the Bacon-Campbell-Hausdorff formula. It is the fact that the Lie bracket and the sum on the Lie algebra, they determine the product on the group. And really they determine via a precise formula. There are other formulas that maybe they're not as famous as the Bacon-Campbell-Hausdorff formula that also give the other implications. For example, there is the Zassenhaus formula that tells you that the product on G and the Lie bracket on G determine the sum on the Lie algebra. And there is also something very general called the Lazard correspondence that tells you that the product on G determines the sum and the Lie bracket and the Lie bracket on the Lie algebra. Okay, so now for this, so let's see what are the first terms that we might use in the Bacon-Campbell-Hausdorff formula. The first terms are important and we might use them. So it's like this. So the exponential of x times the exponential of y. So the first approximation is really the exponential of the sum. And this would be an equality in the case of an abelian group. But then there are other terms. There is 1/2 the bracket. And then there are terms with 3 brackets. It's 1/2 x, y plus 1/12. This is 1/12. 1/12 of y, x plus other terms, but those terms they have at least 4 brackets. 3 brackets of at least 4 elements. Okay. One use of the Bacon-Campbell-Hausdorff formula is to read the product of the Lie group on the Lie algebra. In other words, one can use the exponential map to consider coordinates. The exponential map gives coordinates. So remember that, I mean, this is an obvious fact from the fact that the differential of the exponential at the origin is the identity map. So it's an isomorphism. And therefore, there exists some open set on the Lie algebra, an open set on G, And so the first open set contains 0 and the second contains the identity, such that the exponential map from U to V is a diffeomorphism. In other words, we have put coordinates on a neighborhood of the identity. So, and on the open set U, we can, read the product of G via the Campbell Hausdorff formula. So we can declare that the product of two vectors is the log of Ex, Ey, which for the Campbell Hausdorff formula, this is x plus y plus 1/2 xy plus ... If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.